I couldn't help thinking about what Goiko just said about feedback loops. I'm just about to give a talk that I've never given before, so I have no idea how well it'll go down, but at least I'll get some feedback, hopefully. So I apologize in advance if you just walk out and scratch your head and what the hell was that? So I'm going to talk about something called Petri nets. So my name's Aslak Hellesoy. I've been a programmer for, I don't know, 20, 25 years. I've created a tool called Cucumber, founded a company around that 5 years ago, and we just recently sold that company to SmartBear, where I'm now working, and I'm working full-time on open source. So this is exciting for me because I can do open source, I get paid for it 100% of my time. It's great. And as part of doing that, I wanted to make some changes to Cucumber, make it run distributed and so on, and that's how I started looking at Petri nets. Raise your hand if you've ever come across Petri nets. Not many people, right? Not very surprising. I learned about Petri nets when I went to university in France in the 90s, and then I never heard about them again. But I thought they were kind of intriguing, and I looked them up again. So before I get into Petri nets, I want to tell a few stories that I've come across recently where I think they might have worked. And then I'm going to give you an introduction to what Petri nets are. And finally, we're going to do some test-driven development with Petri nets. And then you're going to walk out the door, and you're going to scratch your head, and you're going to say, what the hell was that all about? And I'll have my feedback loop. All right, so a couple of 6 months ago, I was working on this project, which is a online website for buying contact lenses, and so it's a shopping website. And they were, while I was there for a few months. They were really struggling to model the business process of buying contact lenses. You know, it's if you've ever worked in retail, you know, you've got orders and subscriptions and billing and inventory and shipping and delivery and all those kind of things. And you know, every order goes through a sequence of transformations or steps. You know, there's a whole process happening. And they tried to model this because they were building something new on top of a legacy system, and nobody had a full picture of what was going on. So they tried to model this with a state diagram, which looked like this. And don't worry if you don't see what this is. That's not why I'm showing the slide. But you can see that, you know, that there's lots of states here which are supposed to model a subscription, and lots of arrows and lots of circles and some text. And you know, this was their best shot at describing the whole process of placing an order or making a subscription for contact lenses to be delivered on your door. And you know, they were never happy with it, and that's why they, you know, printed T-shirts, because it was just so frustrating to not be able to express this process. And I said, "Have you thought about Petri nets?" And they were like, "What is Petri nets?" And then I left, so we never really had a chance to explore Petri nets. But I'm going to go have beer with Josh and next week, so maybe we can do some Petri nets in the pub. So the problem with state diagram, well, who's familiar with state diagrams? I guess pretty much everyone, right? So what is a state diagram? It's a way to visualize how a system evolves through different states and what state transitions are valid or invalid in a particular state. The problem with state diagrams is that they don't work particularly well to model a concurrent or a distributed process. Because if you've got a concurrent or distributed process, you know, let's say you've got 3 different systems that sort of evolve autonomously. Well, there's state in all of these things, and that's just really hard to model in a state diagram, and that's why this didn't really work for that team. So they don't really work for distributed, concurrent, parallel systems. But that's not the only kind of stuff they don't work for. Tic-tac-toe. Let's take this game. Everybody knows this game, right? You start with 9 empty squares, and then you can put noughts and crosses in. How many states do you think there are in this game? Any guesses? Like if you were to count all the valid positions that you can have and draw a state diagram, starting with the start node is an empty one, and then you've got, well, the first one's easy. How many states can you get from? 9 factorial. 9. Well, it's 3 to the power of 9. Yeah. Well, that's one way of counting it. You know, if you start with the first one, you've got 9 possible states that you can go to. Or if you've removed symmetry, you can say there's 3. You know, you can put one in a corner, one on the edge, or one in the center. So you've removed symmetry. So depending on how you count, you'll end up with between 765 if you remove all symmetry and stuff like that, and remove all invalid states. Or if you just do a brute force like Goko, you'll end up with 3 to the power of 9, which is, or is it? I can't remember now, but lots of states, right? Lots and lots of states. And as you can see here, this is the state transition diagram for tic-tac-toe. Now, what about your business process? Do you think you could draw a state transition diagram for your business process? Has anyone tried to? Right. Happy with it? Yeah, maybe. It's, you know, depends on what you use it for. I think models they can be used for 2 things, primarily. They can be used for communication, to build a shared understanding of the system, but it's like an informal model. It's something that you just use to have a conversation around. Or you can use it as a validation tool. You can actually sort of connect the model to your system and verify that your system and your model is consistent. Now, this is really complicated, right? So I'm going to show you what the state space of a tic-tac-toe game looks like if you were to use a Petri net, like this. Now, I'm not saying that this doesn't look messy, but it's less messy than the previous state transition diagram. This is a graph, just like a state transition diagram. There's 40 vertices, or 40 nodes in this graph. 21 of them are circles, and 19 of them are rectangles. And then you've got some edges between them. And you see we've got some other things as well here. We've got some dots inside some of those circles. So this is what a Petri net looks like. So you can kind of think of it as a state transition diagram, which can sort of, I can say on steroids, but what does that mean? It's a state it represents the same kind of information as a state transition diagram, but in a much more compact and concise way. And they were invented by this chap here, Carl Adam Petri, which is one of Germany's most famous computer scientists, when he was 13 years old. So I don't know what he was. Well, when he was 13 years old, the only thing I know was that he must have been taking some chemistry lessons. I think he probably wanted to visualize how chemical processes worked. So this is how you can use a Petri net to describe a chemical process. So you start out with a carbon atom and, what is that? Oxygen. And then you have a transition here. Oops, there's a hole here, so don't fall down. You have a transition here that will create CO2, right? And now you can get I can't remember now. What is this? Sodium hydroxide. You combine sodium hydroxide and CO2. You get sodium something else. And then you get hydrochloride. And then you get, now it splits up in water and salt and greenhouse gases. I do remember some things from chemistry. So this is how Carl Adam Petri, at 13 years old, invented PetriNets to describe a chemical process. Now, it turns out that this model is pretty good for describing lots of different kinds of processes, not just chemistry. So over the past 50 years, this has evolved into, into a whole science. There's a solid mathematical foundation behind this. You can model them as matrices and vectors, and use graph theory to prove things like reachability and deadlocks and liveness and stuff like that. So there's a whole lot of research and tooling that's been done around PetriNets to analyze their properties. Here's another one for taking the bus. Did anyone take the bus this morning? I'm sure somebody did. Right. So here's a PetriNet describing the process of somebody getting on a bus. So you've got 3 people waiting here, and there's a bus arriving. And this sort of describes how somebody can get on the bus and how they can no longer get on the bus when the bus has left, right? So I don't expect you to understand exactly how to interpret this. I'll explain what those different things mean. So let's do a PetriNet crash course. And then after that, we'll do a bit of TDD with PetriNet, because this isn't all just theory. Right, so this is just some PetriNet. I don't know what it represents. The first thing you need to know about is the place. So place is a circle. So there's 2 kind of vertices in this graph. There's places and transitions. So what is a place? A place is often a noun. So this can be something like a bus. It can represent a buffer or a queue. It can represent a location, maybe a location in a warehouse, or maybe a room in a hospital, or maybe it can represent a floor if you're modeling lifts, stuff like that. And they can contain 0 or more tokens, which I'll get back to in a minute. So places represent things that can have state. The next thing is a transition, and this is often a verb. So this, I don't know if you remember from the previous one, what did we see here? One person gets on the bus, right? So enter bus. So this is an active node. It represents a reaction or an event or a command, something that's happening in the system, something that will change the global state of the system. And the difference here between a state transition diagram is that you can represent a distributed process this way. A transition can be enabled or disabled, which means it may or may not be in a fireable state. So in order for a transition to be enabled, all of the places that point towards that transition have to have at least 1 token in them. So can anyone identify which one of those transitions here are not enabled? It's this one that I've colored, right? Because there isn't a token here, so I cannot fire this transition. I can fire this one, because all of the incoming places have at least 1 token. So if I fire this one, it's going to move this token over here. And now this one is no longer fireable, but this one is. And you can have several transitions in a PetriNet that are fireable at any given time, which means that you can model it, so it's a non-deterministic system. So that's places and transitions. Tokens. So tokens are inside of a place, and they are moved by the transition. So when you fire a transition, tokens will move from the input places to that transition to the output place. So if I fire this one, if I fire this transition here, it's going to remove 1 token here, it's going to remove 1 token there, and it's going to put 1 token in there. So I've actually removed a token from the entire system. And they often represent a physical object, like a product or a person, or so they're an indicator of state. So they're related to the places, and they represent whether something is present or not in a particular place. And then finally, you've got the arcs, which connect the transitions to the places. You can never have an arc between a place and another place. You can never have an arc between a transition and a transition. They always go from place to transition, and then from transition to place, and so on. So for those of you who are graph nerds, this is a directed bipartite graph. All right, so that's for the theory. So now you have maybe a vague idea what a Petri net is. And some of you are probably feeling a bit like this now, because this reminds you maybe of university, although it sounds like most of you didn't learn about this. I think maybe it was more popular in France than England. I don't know. Maybe it reminds you of waterfall. It does remind me of waterfall. I brushed up on Petri nets by reading this book here. Yeah, reading this book certainly makes me think of waterfall, because this is the kind of stuff that people who like to do big upfront design love to use, right? Petri nets, beautiful. I can design the entire process, and then I can give it to somebody to develop, which is a ludicrous idea, in my opinion, and that's what this book sort of advocates. But that doesn't mean that just because we don't believe in design up front, that we should throw all of the babies out with the bathwater. So I want to just save one baby, and that's the Petri net. And I want to put the Petri net in a non-waterfall big design up front context, which is test-driven development, and I want to explore how that can work. So my approach is, for a process, is not to come up with the entire Petri net to describe the process in the beginning. It's to evolve the model incrementally and have feedback loops between the model and the code and the tests. And before you even start doing this, I would recommend that you have some sort of collaborative workshop between various stakeholders on your project, people who are domain experts, who understand the domain, users, product owners, business analysts, those kind of business people, as well as programmers who understand how to implement stuff, as well as testers who can think of stuff that get wrong. When you put these people in the same room and use techniques like event storming or example mapping, you'll build a shared understanding of the system, which I think is a very useful prerequisite to do before you go in and model. And then you can create a model which you'll iterate on, right? And you can use validation tools to validate that model. I'm not going to show you how to do that. But over here, you can do some TDD. You've got some code, you've got some tests, you do the TDD cycle. And hopefully what's novel in this approach is that you can take the code and the tests and the model and create some living documentation for this system. So you can sort of connect the model to the code, and you will know when the model goes out of sync with the code, or the code goes out of sync with the model. And then you can use the model for two purposes, right? You use it to build a shared understanding of what the process is, like this retail team I was trying to do. But hopefully you can model the process more concisely, and even more importantly, you can link it to the code so you know if it goes out of sync. So what are we going to do? We are going to do something simple, like an X-ray machine. Actually, not an X-ray machine. We are going to do a hospital that has an X-ray machine. Bit simpler. So imagine you've got a clinic or a hospital somewhere. They've got an X-ray machine, and they've got a waiting room, and people who have come to have pictures taken of their body, they wait here. And when this room is empty, they go through this door, have some pictures taken, and then they leave, and then someone else can come in. How would we represent this with a Petri net? Well, let's have a look. And now I'm going to switch to some live coding. So this is probably when things start to go wrong, but we can try. I'm going to turn off my mirroring. There we go. Turn on my mirroring. Right. So I've got this wonderful. Can you see this, or should I make it a bit bigger? Yeah. So I'm going to start up my case tool now. Who loves case tools? Nobody. All right. It's called pipe. Oops. Right. Ah, come on. Really? Jekyll, sorry. It only runs on Java 8, so I need to change my Java version. Right, JHome 1.8. There we go, I'm on Java 1.8. I can run this tool that some researchers created for designing Petri nets and analyzing them. So I've already designed this Petri net, and here it is. I don't know if I can zoom. Is this visible from the back? I think I have another version of it. This one here. Right, let's look at this. I can make this a bit bigger. Right. Okay. So remember this, there's 3 rooms. There's a waiting room, the X-ray machine room, and the, well, outside of the building. 3 locations. I've modeled this with 4 different places, though. So people in the waiting room, you know, the number of tokens in the waiting room represents how many people, sorry, how many tokens in the waiting place represents how many people are waiting. And then we have a transition, which represents somebody going through the door. And now they're inside of that room. The next thing that can happen is that they've climbed up onto that machine, and the picture's taken. And the next thing, so that we have 2 different states inside of this X-ray room, which is like before the picture's taken and after the picture's taken, and then they can leave, right? So we can. This is our first shot at implementing this model, and we can do this collaboratively. You know, we can look at it and it's like, does that represent the process? And people go like, yeah, I think so. You know, at least good enough for now. And now we can start doing some TDD. So I'm using Ruby here, but you can use pretty much any language. You can use any language to do this. Let's just focus on this test that I have here. So it can process 1 patient. So I've modeled the whole system as something called a clinic. They can enter, can make a photo, and then they can leave. Those are the transitions that I have in my system. And then I have some assertions. I expect, well, I set up that initially there's 3 people waiting. And then afterwards, I expect there to only be 2 people waiting and nobody left in the X-ray room, right? So I can run that, and oops. Why does it go bigger and then smaller again? So I can run this. Oh, right, that runs. Now what I can do, let's just change it a bit. So I want to say, oh, that's the wrong one. I want to say, rather than, let's say that we have 5 people waiting. You know, should the test still pass? I don't know, let's see. No, it fails now because, well, I said I expect there to be 2 in the waiting room when I'm done, but there should be 4 now, right? So I can do this. It's green. Now if I run this tool make again, it's going to, did you see that? No, you don't see that. But this is the cool bit. This is where I create the living documentation. So I have this little tool, which is a little tool that I created in order to be able to do sort of test-driven development with Petri nets. This is a tool that creates a visualization of the net for this particular test. So you see, it has 5 in here now. So this is my living documentation. This is an example of how this net works in a particular, scenario. And it loops. So I have 5 people initially. I send 1 person through, and then in the end I have 4. So you see, I've connected my my model to my code and to my test, and I have living documentation. Now, how would you feel if you went to the clinic, you sit and wait, you go inside of the X-ray room, you take off your take off your clothes, you lie down on the machine, and then some dude just walks in. I go like, "Are you going to be done soon?" How would you feel about that? I would probably not be okay with that. So what we want, so there's a flaw in our model here. We should not allow anyone to enter while there's somebody who's having their picture taken, right? So our model does not represent what we want. So let's write a test to express that bug or that bad design. So I'm going to write another test here. Let me see, where is it? Here we go. So I'm going to write a test that I would like to fail, right? So I'm going to say, does not let 2 people into X-ray. It does not let 2 people enter, right? So if I do this, I can even remove that. Would you expect that to pass or fail if the system was behaving the way we want it to behave? I would expect this to fail. This should not be possible, right? So if I run my tests, it isn't failing. And in fact, I'll have a new, where is it? I have a new, this is now representing this example. See, we got 2 people in here. That's ludicrous. 1 person looking at another naked person and they don't know each other. That's just, no. So we've got to put a stop to that. So how can we do that? How can we prevent those people from just walking in? Well, we've got to go back to our beautiful case tool and change our model. Now, any suggestions? Speak up, please. The door only opens when someone leaves. Yep. Right. So what I'm going to do is I'm going to add another place here to, and I apologize that you can't read this from the back, but once I regenerate it with my nice tool, you'll see it. But I'll try to explain. So I'm going to add another place here. I'm going to call that to represent whether or not we are busy. So occupied and free, right? Let's just call it, or, yeah. Not occupied, available. Let's call it available. And I'm going to create another one, oops, here, called busy. And then I'm going to draw an arc from this place to this transition, and then I'm going to draw one from here to here, one from here to here. I mean, this is obvious, right? This is what you need to do. Just joking. The difficult thing about any new kind of modeling tools is that it takes a while before you can figure out how to model your real world in this notation, right? But the nice thing about this tool is that I can simulate here, just to sort of see if I think I've done the right thing. So you see that this red one here is now fireable, so somebody can enter. And look now, there's an available token. There's a token in the available place, right? And as soon as I enter, that token goes away. And because that token goes away, this transition is no longer fireable. Can't fire this one anymore now. So nobody can go in and look at naked people. And we can take the picture, they can leave, and now the interesting thing is that this busy place here will be sucked up by this transition and then sent back here. Boom, like this. So I can save this model now, press save, and just to show you, oops. You know, I've now made a change to my model here. Because this whole PetriNet model is represented in, you know, XML, of course. It's, you know, goes with the culture. Git diff, model, X-ray machine. You'll see there's some extra stuff in here. Now, oops, is that it? Hope so. That's odd. Oh, I need to stop it before I save it, of course. Yeah, okay. This tool is a bit buggy. So now I've changed my model. What happens if I run my test again now? Now, it's failing. It's saying, no, you can't fire enter. So actually, my unit test, or my, you know, if I just run this, that passes. So the test itself passes, but it's when I validate against the net that it fails. So how is this TDD? Well, I created a test that I wanted to fail, but it didn't fail. And then I went to the model to make a change to sort of provoke that failure. So now the model is more correct, but my code isn't. So what I can do now is I can go and update my test. And say, actually, I expect an error here. So I can do, how do you do that again? Expect, I think it's like this. Any Rubyists here? I used to be one of the maintainers of RSpec, and I can't remember how to use it anymore, because to raise error? Is it like that? With some sort of message saying enter? I don't know. But nothing was raised. Right, okay. So now, I need to go and change my code. So now I need to go in here and say enter. Okay, so this is my very, very simple embryonic code in here. So when I say enter, I need to throw an exception here if there is already one in the X-ray room, right? So raise. If X-ray room greater than 0. I think that's right. Ah! Cannot fire enter. All right. So I still got some work to do, but I think you get the gist of it. So I'm going to show this again. Yes, because I didn't quite finish the code. It's still showing the illegal state, but once I've fixed up my code, this would have not displayed the second person coming into the room, and I would have had a model that's in sync with my code, and I've done the whole thing with TDD. So that's it, really. I'm really inspired by this book called Living Documentation by Cyril Martrère. It's in my, I'll show you the references that I have at the end here, which is this book down here. Oops, second last one, which is essentially a book that shows you how some principles and techniques that you can use to generate living documentation from your code and do it in a way that makes sense for your project. So there are no standard kind of diagrams. Petri nets might work well if you've got a very process-heavy system that you're working with, but you could also do state diagrams. So I guess the takeaway from my talk is experiment with different kinds of modeling systems and see if you can find a way to connect them to your code so you can use them both as a validation tool and as a communication tool. And don't aim to make those models perfect from the start. Start with something small and evolve them, and use the feedback that you get from all of the things in your system, whether it's conversations, models, tests, code, to improve things. And that's it. And I'm ready, I think, for a few questions. Okay.
How easy it is to represent Petri net diagrams statically rather than animated?
How do you represent Petri net statically rather than animated? Just one picture. Right. So the value. So Petri nets, they are good for describing behavior. And what's behavior? Well, behavior is things changing. So, and that's why I think it's useful to display them as animated. In this case, I'm using animated GIFs. So I could just show, a snapshot, but then it wouldn't have the same value as communication, because what I want to see is how things evolve and whether you end up in a valid or an invalid state. So you could just take a picture of one of those states and have that, but I don't think it would have the same communication value. Question in the back?
Yeah, I saw that you are using the transitions, and some of the transitions were having more the arch coming out and coming in. What happens when you are doing such a transition? Does, for example, if you have only one token and two outgoing arcs, does the token duplicate, or does you have to have two tokens?
Let me go back to this one here, which is a sort of generic one. So when you fire a transition, well, first off, in order for it to be fireable, all of the input places, so that's all of the places that point to the transition, all of those places have to have at least one token, right? When you fire the transition, you remove a token from each of these places. So you may have 100 places going in, or let's say you have 5 places going in. You remove a token from each one of those 5 places. And then for each of the output places, you put a token. So you may have a transition that has 5 input places and 2 output places. When you fire that transition, you're going to remove 5 tokens from the input ones, or remove a token from each of the 5 input ones, and then you're going to put a token in each of the 2 output ones. So the number of tokens in the system is not constant. It will change. It depends on the topology of your net. You can also have weights on the arc, so you can say the default weight of an arc is 1, but you can say 2, for example, and that means if I say that the weight of this arc here is 2, you know, this would only be this would only be fireable if if there's at least 2 tokens in this place, and then after I fired it once, it wouldn't fire it again. Does that answer the question? Yeah.
How does your validation tool work, I guess, specifically? Like, is it parsing your unit tests or something? Or, like, what's that interaction?
The one that I created to generate those animated GIFs.
Yeah, and
right,
how
yeah.
does that interact, like, with between your code and your unit tests?
Yeah, so I've written a little tool that generates this, right? And it reads 2 things as input. It reads the topology of the net, which is just an XML file.
That's what was generated from the other tool.
That's just generated from the case tool. There's many different tools you can use to generate this. And this is static, right? This doesn't really change. But then it uses another file as input, which is this file. And this file is generated while I'm running the test. So this is sort of like a recording of what happened. And this is just a very, very simple DSL that I made up for the purpose of this tool, but it has, if a line has a colon in it, it's an initial marking. So that's just for placing the initial tokens. And then each of the other ones are the transitions that are firing. And I feed this through the little tool, and if I try to fire a transition that isn't valid, I get an exception, and it dies. But the interesting thing is that, you know, I did this now with TDD. But you can have a model, and you can have a live system running somewhere which prints out a bunch of logs when stuff happens, and you can write a tiny little tool that would pull the interesting bits out of those logs and generate a file like this. And now you can validate the behavior of a live system, which might be distributed, right? You can pull logs from 10 different locations and generate a file like this that represents the interesting events and validate against the model. And that's a great way to find out whether whether there's a flaw in your model, or maybe whether, you know, deadlocks, stuff like that. And that's something that I haven't tried yet, but I would if somebody tries that, please let me know, because I think that'd be very interesting. All right, I think we're out of time. Just feel free to grab me if you have any more questions.
Thank you.
Thank you very much.